Okay, so yeah, we start, Guy.
Yeah, okay, we'll start maybe a little bit slowly and then continue faster. So we'll start maybe by recalling. I I will I will not assume that you remember much from last week. Uh, so at least that's the goal. So I say recall, but if it's the first time that you see this, this is probably going to still be more or less okay. So we wanted to prove a theorem that says that non-deterministic exponential time, any language in non-deterministic exponential time has a multi-prover interactive protocol with just two provers and just a single round at a soundness of 1/2. So an instance for this language will be accepted with probability at most 1/2 if it's not really a true element of the language. So that's what we wanted to prove, but by a series of reductions, we reduced to the following claim. So first of all, there was this problem called succinct 3-sat, which is complete in non-deterministic exponential time. And that we want to prove that it belongs to multi-low degree polynomial oracle proof with soundness that is somewhat separated from one and a number of provers that can be polynomially large. So this means that we have the verifier and he has this instance that he wants to verify that he wants to verify that the instance belong to succinct 3-sat, and he has access, he can send one question to each of I don't know, some number of polynomials. Yeah, so these polynomials just lie there in space, and it can, in boxes, and the verifier can send an X to some polynomial and receive its evaluation at X, and it can do it in parallel to all polynomials, and then it needs to decide whether he accepts the instance or not. And if it is a true satisfiable succinct 3-sat instance, the verifier should accept with probability 1. And if it's not, then he should reject with at least 1 over polynomial probability. That's all we want. Okay, and so that's what we are going to prove today, hopefully. Here are the steps that we are going to take. We have to take steps. So one of them is called arithmetization. That's a long word, so that's the last time I'm writing it in totality here. So the arithmetization means taking, so it translates the claim that the instance belongs to succinct 3-sat to a statement about low degree polynomials. So it makes sense that this would be a step towards our goal, because we want to verify something using polynomials. So it's easier if the claim itself is translated into a claim about polynomials. So that's the first step. And the second step is use our ability to access polynomials to verify the claim. Yeah, and here is a good point to say that just stop me wherever if you have questions, or if something is not clear, or if you want to point something out, whatever. Okay, so let's start with arithmetization. How do we arithmetize? Yeah, that's enough. How do we arithmetize a statement about some instance belonging to the language of satisfiable succinct three-sat instances? Yeah, so for that, we should probably remind ourselves what is succinct three-sat and how it is given to us as an instance. So given a succinct three-sat instance, which is a formula, maybe f of size maybe n. Actually, maybe I should mention this is a Boolean formula. So yeah, so this is how a succinct three-sat instance looks like. I have a Boolean formula. So it is given to me as these gates of ands and ors and nots. The input to the formula has several kinds of variables. So we have m variables to name a clause. We have, sorry. We have three indices of variables, and we have the values of the variables themselves. Yeah, and the output of the formula is just 0 and 1. All right, so we have a formula which defines a Boolean function of this form, which represents three CNF, basically three-sat, but it's actually a little bit more general than that. Formula phi, which is defined as follows. Phi takes the first kind of, so I is this one. We should think of it as an index of a clause, and then we have alpha and beta and gamma. So these are the three indices of variables, and then it takes the values of these Boolean variables. Yeah, sorry. All this, yeah, sorry. Let's begin again. Phi only depends on the assignment to two to the L variables. So phi is a function of x1 up to x2 to the L, and it's an and I in 0, 1 to the m. So again, I is like an index of a clause, but actually we don't know which variables the clause depends on. So we go over all possible alpha, beta, and gammas, each in 0, 1 to the L. So all possible three indices of variables. And then we take f of I and alpha and beta and gamma. and X with index alpha and X with index beta and X with index gamma. And that's our clause. So this is a function of 3 variables in the assignment to the variables for phi. So we have a very large exponentially sized end of functions of 3 variables from the assignment. So this is a big end of clauses, and each clause depends on 3 variables. So that's how a small formula can represent a huge exponentially sized formula containing exponentially many clauses of 3 variables each. Right, so this is, and yeah, so the statement is that there exists, just a second, there exists an assignment from 0, 1 to the L to 0, 1. So this is an assignment to the variables of the formula phi. So A represents an assignment for these x's, such that all of the clauses are satisfied. So here's a way to write it. For every I in 0, 1 to the m, and every alpha and beta and gamma in 0, 1 to the L, it holds that f of I, alpha, beta, gamma, x alpha, x beta, sorry, I need to use the assignment here. So the assignment to x alpha is A of alpha, the assignment to x beta is A of beta, and so forth. That equals 1. Okay, so this is the starting point for the arithmetization. I want to take this statement. So this statement is a statement about a Boolean formula, and I want to transform it into a statement about polynomials. So are there any questions so far?
Everything would be over a finite field, I suppose, right?
Right, yes. So yeah, so the so the way that I will do it is I'll pick some finite field that somehow contains 0 and 1, like in every field. And then I will translate the formula f, which is a Boolean formula, into an arithmetic formula over the field that identifies with f on assignments that have only values 0 and 1, or that only have entries 0 and 1. So that's the main idea. So first step would be picking a field. And that is very simple. So choose prime P, which is big enough. So it should be bigger than n. This is the size of the formula f. And it should be bigger than L. L is the log of the number of variables of the formula phi that f encodes. Yeah, so pick P to be, yeah.
Is it okay to pick 2 to the power such that this is satisfied?
Yeah, actually any field of size significantly larger than that would work.
Great, thanks.
Right, yeah, so that's just an example of one thing that you can do. Actually, all I care about is the size of the field. And note that this is the size of P is polynomial in all the parameters in the input. So N is the size of the input, the size of the formula, and L is smaller than N, is smaller than the size of the formula because the formula depends, among other things, on 3L different variables. These are the indices of the variables. So this is a polynomial size field, and just take F, our field, and that's the field that we're going to fix from now on. This is going to be the field of size P. And again, it could be any field, any finite field of appropriate size. Okay, so that was easy. And then let's arithmetize the formula F. And that's also pretty easy. So F is a Boolean formula of size that you already know. It's a Boolean formula of size n. So it has gates such as this one. This is an AND gate of 2 inputs. If I want to represent an AND gate using an arithmetic operation, I will just use the multiplication of the same inputs, right? And I want to do the same for every other kind of gate inside F.
And this is because you only care about 0, 1.
Right, yes. So the property of this translation is that when the inputs 1 and 2 are Boolean, then the output is the same here and here. So maybe I will write it. Output is same for Boolean inputs. So that's the property that I want to keep. Yeah, so the other kind of gate that I want to take care of is the NOT gate. And the NOT gate, I can, well, that's pretty easy. NOT of x is the same as 1 minus x for x, which is 0 and 1. So all I want is to, yeah, so let me not call it 1, let me call it input 1. So I want 1 minus input 1, and that I will get by taking the plus. Here I will take 1, and here I will take the product of input 1 and minus 1. Right, so given the input I1, here I get minus I1, and here I get 1 minus I1. Right, and I need to do this, at least in principle, I need to do the same for the OR gate. Instead of showing you how to translate the OR gate, I will tell you that the OR gate is the same as taking the end of the NOTs of the inputs.
So, Guy, is it important for you that the field is not of characteristic 2?
No, actually, it's not important.
I think that even in the quantum case, they need it at some points, that the fields that we work over are of characteristic 2.
So I wrote -1 here. And of course, if the field is of characteristic 2, -1 and 1 are the same thing. But indeed, 1 plus I1 is the same as the NOT of I1 over a field of characteristic 2. Right, and the OR gate, I can first translate it to an AND gate and some NOT gates, and then continue.
Use Morgan. Use the Morgan.
Sorry?
Use the Morgan.
Yeah, this is the Morgan. Yeah, this is a, yeah. Right, so yeah, so that's easy. I just transform all the gates from Boolean gates to the appropriate arithmetic gates. We get a formula. So f hat, it's now an arithmetic formula. But as a function, it's a function from f to the m plus 3l plus 3 into f, where before f was the same only with 0, 1 instead of f. And the degree of f hat is at most the size of the original formula. That's because if you look closely, you will see that negation doesn't increase the degree. If the input was a polynomial of degree d, then the output here would also be a polynomial of degree d, because we just multiply it by a constant and then added a constant. Here, the OR only adds an AND gate, and an AND gate, what it does to the degree is sum the degrees of the inputs, right? Because we just multiply the two inputs. And if we assume by induction then that the inputs are polynomials of size that is bounded by the size of these sub formulas, then together I get, after multiplication, I get a polynomial whose degree is the sum of these, which is bounded by the size of this new sub formula. Right, so by induction, the degree of the new arithmetic formula is bounded, yeah, so the degree is bounded by the size of the original formula. Is this okay so far? Okay, so that's one thing that is important to note, that the degree of the new formula is polynomially bounded. It's bounded by n. There's another thing that I want to note here is that f hat can be easily evaluated at each point in polynomial time.
Guy?
Yeah.
About the previous point, actually, you know a bit more, because the fact that you took Boolean function means that this is a multilinear polynomial, right? Like
yes.
In every monomial, the degree of each variable is at most 1.
Not really. So it's a good observation, but somehow, so it's true that because f prime, f hat is sort of an extension of f, right? So here's something that we already said, but I can write it here again. F hat, if we only look at inputs m plus 3l plus 3, if we only look at 0, 1 inputs, it's the same as f. And what Michael says is that such functions over Boolean inputs, they can be extended with multilinear polynomials. This is true, but the way that I extended f using f hat was not by using any multilinear polynomials. It's by the way that I just showed, by replacing gates.
Yeah, I understand, but okay, so maybe when you defined what f is, you said that every variable is used only in one of the gates, and then it is used only using the output of this gate, right?
Okay, yeah, that's a good point.
So I think the
wait, let me correct you and then you'll see. So yeah, if this were the case, then you would be right. But it's not, because it's, you know, the fact that it's a formula means that the output of each gate is used by only one other gate. What is not true is that each variable is used by at most one gate.
so the original variables can be used in multiple gates?
Yes, each variable can be used in multiple gates. So you have like one layer where, yeah, where you have like multiple fan out, but then in every other level, it's fan out one.
Yeah, because last time we talked about trees and so on, and so this is not a tree.
So we said that it's a tree except for the access to the variables.
Okay, thanks.
Is it really the same label can appear in different leaves?
Yeah, that's another way to say it. Yeah. Yeah. So either you have the labels of variables on the leaves, and the same label can appear in many leaves, or you have each variable appearing once, but then it can be connected to multiple gates. So yeah, so I don't get necessarily a formula for a multilinear polynomial, but still I get a formula whose degree is bounded by n, by the size of the original Boolean formula. And that is an important point. Right, so I replaced a Boolean formula by an arithmetic formula that computes some polynomial of smallish degree, bounded by n. And that's it. That's the arithmetization of the formula.
But also, we never spell out what f is, right? We only keep it in this form.
What do you mean spell out?
Coming back to Michael's remark, you could, I mean, if you had written out the polynomial as a polynomial, then you could have eliminated higher degrees, but we never do this.
Yes, I could, in theory, write out the formula for f and then kill all the degrees that are bigger than 1. But it would take exponential time. And even after I remove, even after I remove all the degrees higher than 1 in each variable, the size of the formula that I would get could still be exponential, because there are, due to the number of variables, many multilinear monomials. So yeah,
okay.
so that is something I want to escape. I want to be able to transfer a Boolean formula into a polynomial formula, but without expanding everything out. I want to be able to do it in polynomial time. Yes, Michael.
Okay, I'm okay with everything up till now, but I know for like a curious, I don't know how to say it.
Curiosity.
Okay. That there should be a way of just handling multilinear polynomials. This is just something I heard. I don't know how, because I'm seeing the proof for the first time.
That happens in the IP equals P space proof, but that's a different.
You say that in the MIP you cannot use only
no,
multilinear?
if you want to someone to be able to evaluate it. Computing a coefficient of the multilinear polynomial is a hard problem.
Okay.
Okay. Yeah, so things are delicate here because I'm dealing with polynomial-sized formulas that if you open them up, they become exponential size, and we don't want to deal with exponential size. We want to be able to evaluate f hat, the arithmetization of f, at any point in polynomial time. So instead of being pedantic and making the degree in each variable linear, it's enough to just do this crude translation, and then I get from a formula of size n, an arithmetic formula of size linear in n, and it computes a polynomial of small degree, and I can evaluate it anywhere I want in polynomial time. So fine, that was the arithmetization of the formula. Now, remember, I want to arithmetize this statement, which says that there is an assignment such that the formula something. So this part we already arithmetized. The next thing I want to arithmetize is this statement, that there exists an assignment A. I want to transform it into a statement about an existence of a polynomial.
Guy, sorry that I'm taking you back. I wasn't, לא הייתי מרוכז. The fact that you can calculate it in polynomial time is related to the fact that f, that can you interpolate from a small amount of points?
No, it has nothing to do with that. So let's remember what f is. F is a formula that has m.
No, big F, I remember what big F is.
Okay.
I'm asking about the polynomial. The fact that you can evaluate it at points that are not in the cube. This comes from interpolation?
Just follow your nose.
No, I
It has a
have.
factorization.
You go through the Boolean function. Great. You arithmetize
Just
any
plug in
gates.
values which are not 0 and 1.
I have a formula for f. It's just a bunch of gates. I translate each gate to a multiplication or one minus something. So now I have an arithmetic formula. And arithmetic formula, I can plug anything I want at the bottom, and out comes some number in the field.
Yeah, great, thanks. This was my confusion.
Okay, all right. So now, so I started with the formula and then ended with an arithmetic formula, and I can use it to compute at any point that I want. The question is now, the next question is what to do with the assignment. I want the statement to be not over Boolean assignments, but over some polynomials. So the next step is to arithmetize the assignment A. So I want to take an assignment A that is defined over, like, given an indices, given an A is given, I'll just write, A is given an index of a Boolean variable and outputs an assignment to this variable. And I want to translate it into something that can be written as a polynomial. So here is a lemma that says that I can actually do that.
Sorry, Guy, why? Maybe I missed it probably in the beginning of the talk, but why do you want to move from an assignment to a polynomial for the assignment?
So this is part of the big problem, a program, sorry. So I have this statement, which is a statement, a Boolean statement about a Boolean formula. There exists a Boolean assignment to the variables such that for every something, the formula outputs 1. And I want to be able to verify the truthfulness.
This statement is under what conditions?
There are no conditions. I get f is this instance that I get. So I get a succinct 3-sat formula f. And someone gives me f and tells me, look, this f represents a huge formula which is satisfiable.
Okay, under the assumption that it's satisfiable.
Yes.
No,
right.
great. The whole thing is to translate a statement about satisfiability of Boolean formula to some property of polynomials.
Right, but I don't understand exactly.
We want to speak in the language. We want an equivalent statement about polynomials.
Right, but I want to hear what Guy wanted to say about specifically about the assignment. Why do you want to move?
Okay, so I have f is something I got. That's my input. And f encodes this huge 3-sat formula. And the claim is that this formula is satisfiable. So it says that there is an assignment such that this is 1 for all the clauses. Now I want, the proof will be by giving me access to some polynomials, to some low-degree polynomials.
Okay, so it's basically a concatenation of polynomials. You're given the assignment as a polynomial and you will apply.
Yeah, so eventually what will happen is that I will be given the assignment as a polynomial, and maybe I will be given some helper polynomials that I can access. And using one access to each such polynomial, I need to be able to verify that this statement is true.
Okay, good.
Okay, so first I translated f that I got to as an input to a polynomial. And now I want to tell you what polynomial I want access to, which will somehow encode the assignment A. Okay, and for this, I need a simple lemma that says that for every, if I have a function over Boolean inputs that has Boolean outputs, then there exists a unique extension of that function to a function f hat that will take values in the field and output values in the field, but will be the same as f on Boolean inputs. So first property of f hat is that f hat on Boolean inputs will be the same as f. And the second property is that f hat is a multilinear polynomial. Multilinear. Okay, so this f hat is called the
choice of notations, right?
What?
F hat is usually Fourier transform.
Yeah, sorry. So that's now it's not a Fourier transform. Now it's the multilinear extension of f, which is a special case of low degree extension. It's an extension to f to a multilinear polynomial. Yeah, so I hope the lemma is clear. The proof of the lemma is also pretty simple. So let's start with showing that there exists this multilinear extension. And this is by noting for a y in 0, 1 to the k, if I want the function delta y, the function that only has the value 1 on y and 0 everywhere else, I can get it by taking the product. I goes from 1 to k of delta yi of xi. So delta yi of xi is the function that has the value 1 only if xi equals yi. So that is clear. And also I can take delta yi of xi to simply be xi if yi equals 1, right? Because xi is 1 only when xi equals yi in this case. This is for Boolean inputs. And 1 minus xi if yi equals 0. Right, so this function satisfies that delta y of x is 1 if x equals y on 0, 1.
Guy, there is a redundant I in the first product. Delta y without I.
No, I want delta of yi of xi, which is 1 if xi equals yi.
To the product over the I.
The next one are inconsistent.
Sorry?
No,
What's
it's fine.
inconsistent? That's a function of of k Boolean variables, and that's a function of one Boolean variable. It takes xi and it outputs 1 if and only if it equals yi.
Okay.
I think the indices are okay here. Right, so this function is 1 for a particular Boolean input and 0 for all other inputs. And so these span all functions on Boolean inputs. In particular, they span f. So I can get f as a linear combination of these things, and these things are very easy to see that they are multilinear functions of x. Right, so this is why there exists a multilinear function that agrees with f on all Boolean inputs. The uniqueness, I don't need it here actually, but I will need it soon. So yeah, why is there a unique multilinear polynomial that agrees with f?
Maybe we need to check the dimensions and see that they are the same.
Yeah, exactly. Because of dimensions. Multilinear polynomials are spanned by the multilinear monomials. And there are exactly 2 to the L multilinear monomials. And there are also exactly 2 to the L dimensions for functions over 0, 1 to the L. So yeah, so uniqueness is because of the dimension. Okay, so now I have this lemma which says that there is a unique multilinear extension, and now given A, well, now I know how to get A prime from A. A prime will be a function from F to the L to F that agrees with A on all the Boolean inputs and is a multilinear polynomial. And something, what else do I need to know about A prime? So the degree of A prime is bounded by what?
It's a, you mean the total
Yeah.
degree? Yeah, by the number of variables.
By the number of variables, yeah. It's just, you know, to see that you are with me. Yeah, it's bounded by L because it's a multilinear polynomial with L variables. And something that we should note that given the input F, we cannot compute A prime because we don't know A, and that's the whole problem. Well, that's not the whole problem, but that's part of the problem. So we defined A hat, but we don't have access to it without help. But at least now we have a statement about polynomials. So now we can rewrite the claim. Actually, maybe we should have a break. So yeah, so I will show you the
maybe
claim
just
again.
just show the reduction. What do we want to prove about these polynomials, and then we'll take a break. Or it will take too long.
It will not take too long, but I think it's a good exercise. I will show you where is the original claim. Here is the original claim. Here is the original statement. So now maybe as an exercise, you can think of how to write this statement in terms of polynomials, now that we have a polynomial version of F and a polynomial version of A. Yeah, so now we are on a break until 5.
How long? Who's running the schedule?
Yeah, 5 is good. So let's meet back at 5.
Right?
Yeah.
Couldn't really understand your uniqueness proof. What is the dimension of how is the Boolean functions in L variables a vector space over F, not F? I mean, you said compare dimension.
Okay.
No, I think that
okay. Here is the formal statement. So look at a multilinear polynomial. I want to define a projection over multilinear polynomial. So you take a multilinear polynomial over the field, and you get from it a function over 0, 1 to the k, just by restriction. So that's that's a projection.
Okay.
Yeah, and it's a linear projection, right?
Mm-hmm.
So it's a function from functions. It's a projection from functions over f to the k to f to functions from 0, 1 to the k to f.
What do you mean linear here? Linear over f2?
No, a linear over f. Linear over f. Right? We are looking at the set of functions from some set into f. The set doesn't need to have anything to do with f.
So maybe, can you show me the statement? Maybe then I didn't see it. Okay, I see what you mean. Okay, בסדר. Thank you. Okay, I think I understand what you mean. Thank you.
Guy?
can I ask something?
I think he froze. Let's wait a few minutes.
Maybe we should state the question in English and explain it in English.
So I guess the question was whether we really need a hat to be multilinear, since at least for some functions, it seems that we get a function that is, just one, for example. Yeah, if the function is fixed to be one, then we get one. And my answer is, first of all, one is fine. One is a multilinear function of degree 0, but it's fine. And my second answer,
but it's not. But if I multiply by scalar the input, the output isn't multiplied. So how is it like multilinear? If I
multilinear
if I multiply
function,
one of the
I see. Okay. Yeah, a multilinear function is not linear. A multilinear function, f is multilinear.
Shouldn't it be linear in one input if I fix the other ones?
Yeah, if you fix the other ones and you multiply one variable, then, or not multiply one variable. If you look at it as a function of one variable, it needs to be an affine linear function. So basically, multilinear just means a sum over some coefficients of monomials of the form x1 times x5 times, I don't know, x6, that's it. Things like that. Okay. But also, I don't really need a hat to be multilinear. All I need is for it to be a low degree polynomial that agrees with A on the Boolean inputs. It just so happens that there exists such a low degree polynomial that is multilinear, but I don't really use strongly this fact.
Okay, thanks.
Okay, so now let's paste here the original statement, and let's try to find how it translates now that we are that we arithmetized everything. So yeah, so here's an equivalent claim. I will actually okay, so instead of saying that there exists an assignment A on these Boolean Boolean vector of indices, I will write there exists this A hat, which now is a function from F to the L to F, and it is of degree at most L. Okay, so that's the first part. And then I need a such that. And I will write it in two forms. One is the like immediate translation, and the next one will be the one that I really want. The immediate translation would be that for every I in 0, 1 to the m, and alpha and beta and gamma in 0, 1 to the L, I have that f hat. Remember, f is my input, but in polynomial time, I can translate it to f hat. So I have access to f hat. I can write it down of I and alpha and beta and gamma and now and a hat alpha and a hat beta and a hat gamma, all this equals 1. Okay, so that's a direct translation, except instead of functions defined over Boolean inputs, I wrote functions that are actually low-degree polynomials. But now I want to think of maybe call it phi hat. I want to define this phi hat of I and alpha and beta and gamma sorry, what do I want? What I really want is to think of this as a function over the field. So maybe I will not try to mangle with this phi. I will just call it so f hat composed with a hat is just the function f hat, where it's a function of only I, alpha, and beta, and gamma. And in the other variables, I just put a hat of alpha and beta and gamma. So that's a function.
Okay, you mean that it takes a quadruple I, alpha, beta, gamma and returns the 7 tuple
Right.
I, alpha, beta, gamma, a hat, alpha, a hat, beta, a hat, gamma.
Right, it takes I and alpha and beta and gamma, so m plus 3L variables, all in F, and outputs something in F. Right, so if now that I define that, I can replace this line by saying that such that this function f composed with a on the Boolean inputs, so 0, 1, on 0, 1 to the m plus 3L is always 1.
So sorry, Guy, why do you say this is equivalent claim? I mean, if you know the existence, if you know the existence of a hat,
okay, no.
How do you deduce the existence of a?
Oh, if I know the existence of a hat, I get a by just restricting a hat to the 0 inputs.
So you assume that a hat has 0, 1 values when you get Boolean input? It's part of the...
Sorry. Yeah, you're absolutely right. I needed to write that down explicitly, which I forgot. So yeah, such that a hat on the 0, 1 inputs is always in 0 and 1, and all the rest is also true. Yeah, I had to, I was supposed to write it down I forgot.
Okay, thanks.
Okay, so now, yeah, so now the statement is there exists this polynomial. We know that actually there's a multilinear polynomial, but anyway, it's a polynomial of degree at most L, which is an extension of a Boolean assignment because it's in 0, 1 for all 0, 1 inputs, such that this polynomial, if we compose it with f hat, we get something that is always 1 on 0, 1 inputs. Okay, so now this is the statement that we need to be able to verify by using access to some polynomials that someone gives us. Questions? Okay, so let's try to imagine how the proof would work. So this is the verifier. The verifier has the formula f, the Boolean formula f as input. The verifier can, in polynomial time, compute f hat. But then he needs to verify that there exists this a hat such that this happens and also this happens. So one thing that the verifier can ask for and should ask for is an oracle for a hat. Right? If there exists an assignment, then the prover should be able to supply him with a polynomial a hat, a low degree polynomial that somehow encodes the satisfying assignment. But he may also ask for access to other helper polynomials that will help the verifier verify the statement. Because for now, what he can do is just access the assignment a hat at one point, and that's it. Yeah, so obviously he needs some additional help. But let's see what he needs to be able to verify. So what do we need to verify now? If we already have access to a hat. So, well, two things. One is that a hat is in 0, 1 for Boolean inputs. And two, well, we already wrote it, but I'll write it again anyway, that f hat composed with a hat on the 0 inputs, on the 0, 1 inputs is constantly 1. Right, so I have access to a hat, and I need to be able to verify both of these things. Let's start with a simpler question. So here is a simpler question. Suppose we are given access to some polynomial f from fk to f. What? And this is a polynomial of degree at most d, and d is small. How do we verify, using additional polynomials, if we are interested, that our polynomial f hat on the 0, 1 inputs is always equal to 0. So suppose this is the simplified statement. Instead of access to a hat, I have access to f hat. I'm guaranteed that f hat is a low-degree polynomial, and the statement is that f is 0 on all 0, 1 inputs. How do I verify that? And that would be actually the key to verifying both of 1 and 2 from above. So, yeah, any ideas from the audience?
It's inductive trick, no?
Sorry?
It's this inductive trick that played in the IP equals P space, no?
No, it's a different trick. It's not the trick from IP equals P space.
You don't have n rounds.
Yeah, there are no rounds. Yeah, so no, if anyone ever saw the IP equals P space thing, what they did there is just there is a trick in which if I have n rounds of interaction with a prover, I can verify that the sum of the values of f on 0, 1 to the k is 0. And if I want, I can actually do the sum with coefficients. So I can choose like these random coefficients and verify that the sum is 0, and except with very small probability, this only happens if f is equal to 0 on 0, 1 to the k. But now I don't have multiple rounds. All I have is access to helper polynomials that I may choose. I mean, I can choose what to ask the provers to give me access to. So the key is a statement called a combinatorial Nullstellensatz. And because I don't know what Nullstellensatz means, I don't know what's combinatorial about it, but I will just...
Nullstellensatz is zero's location.
Yeah, zero's location that I can gather, but what, yeah, but what does it mean?
There's a Hilbert Nullstellensatz, which is very fundamental in algebraic geometry. These guys, Noga mostly.
Right, yeah. So I know all these statements, but how to translate from the word Nullstellensatz to these statements, what is the actual mapping, I'm not sure. But anyway, never mind, here's a statement. So here is a combinatorial null other things statement. Yeah, claim. The claim is the following. It just gives a sufficient and necessary condition for a function to be 0 on the Boolean inputs. So if I have this low degree polynomial and on 0, 1.
Guy, do you want me to say a word about Nullstellensatz? Because I think I can see the similarity. It's very fundamental. But if it takes too much of your time, then I'll skip it.
Let me first write down the statement, and then we can discuss a little bit about Nullstellensatz. But anyway, well, there's, it's obvious that there is some null here. We are talking about a function being 0. So f hat, because it's a polynomial, so f hat is 0 on 0, 1 to the k, if and only if there exist polynomials f1 up to fk. Of course, these are going to be the helper polynomials that I will ask the provers to give me. So there exist these polynomials. The degree of fi is at most d minus 2 for every I, such that f can be written, f of x1 up to xk can be written as a sum I goes from 1 to k of xi times 1 minus xi times fi of x. So what is going on here? Let's look at the easy part first. So if all the coordinates are either 0 or 1, then all of the summands here will be 0 because either xi is 0, in which case this will zero out the summand, or xi is 1, in which case this thing will be 0. So for all Boolean inputs, this thing is 0. And what the claim says is that every polynomial of degree d that is 0 on the binary inputs, on the Boolean inputs, is of this form. And I think generally these Null-Stellensatz things are like structure theorems about polynomials that are zeroed in some set or something like that. Is that true?
Yeah, it's very much in the spirit. So what it says, you have a collection of polynomials. Let me not go into the details. There has to be over an algebraically closed field, but a collection of polynomials, and another polynomial vanishes whenever all these polynomials vanish. Then the theorem says that the reason that such thing happens is trivial, that it's a combination of these original polynomials, perhaps raised to a powers, perhaps with coefficients that are themselves polynomials. So it's like here. I mean, in this situation, the f vanishes together with all those guys. There is nothing else. This is what the Null-Stellensatz theorem. This is the basic thing that makes it possible to define an algebraic variety, blah, blah, blah. The whole thing starts from there in some sense.
And all you need here is just that the field will be large enough.
Okay. So if there are no questions, I will prove it. I will at least say how to prove this claim. And one direction is easy. If f is of this form, then obviously on every Boolean input, it will give 0. So that's just easy. Now, how do you prove it on the other side? Well, you need to be able to divide polynomials with residue or residue, I don't know how it's called. Remainder. So iteratively divide. So take this f minus sum xi1 minus xi fi, I goes from 1 to j minus 1. Okay, so suppose I found fi's for I that goes from 1 to j minus 1. I'll tell you how to find fj. Okay, so I will look at the remainder of my previous endeavors, and I will divide that by the polynomial xj times 1 minus xj as a polynomial in xj. Right, so I don't need to know very fancy algebraic stuff, just how to divide one polynomial in a single variable by another polynomial of the same variable. So I look at this thing. This is a function of many things, but I look at it as a polynomial in xj, and I divide by this thing. And I get, we get that fj as a result plus some remainder. Which I will for now not think about. So, right, so, okay, actually now I want to think about it. Suppose I divided this polynomial by this, by xj times 1 minus xj, I got a remainder which is a polynomial in many variables, among them xj. As a polynomial in xj, what can we say about the remainder?
xj isn't there, or?
No,
It's
3
linear.
plus d minus 2.
It's linear in xj. That's the point that I want to make, right? Because this is how division works with remainders. I divided by something of degree 2, so I get something of degree 1. So the remainder is linear in xj. And in the next iteration, when I divide by xj plus 1 times 1 minus xj plus 1, this will not change. The remainder, I start with a polynomial that's linear in xj, and I will get a polynomial that's still linear in xj and also linear in xj plus 1. So eventually, we get f equals sum xi 1 minus xi times fi plus a remainder, and this is multilinear.
Okay, it's not the same. It is. Okay, never mind. It is
Okay.
multilinear.
Right, so it's a multilinear polynomial in all of these variables. And also, what can we say about...
Sorry, I didn't understand. What's the degree as of in terms of xj of f?
F, I don't, all I know about f is that it is of degree d. So, yeah, and so this thing is something of degree d in xj. But then I divide it by this polynomial of degree 2 in xj. What I get is a polynomial of degree d minus 2 in xj, plus a remainder that is of degree at most 1 in xj. So these polynomials, these are, whoops. These polynomials, these are of degree d minus 2 at most. But R, the remainder, is only of degree 1 in each of the variables. And there's another thing that I know about R, which is that R on Boolean inputs is 0. How do I know that?
It is sustained throughout the divisions, right? Also, always if the original polynomial and the thing you divide with.
The first sum vanishes.
Yeah, because
vanishes, the middle guy vanishes, so the last one vanishes.
Yeah, so f is equal to 0 on Boolean inputs, and this thing is equal to 0 on Boolean inputs on Boolean. And so this one has to be also equal to 0 just to justify the equal sign. So I have a multilinear function that's 0 on all the on all the Boolean inputs. Now I use the uniqueness from before. So this implies that R is just the 0 polynomial. And that finishes this combinatorial Nullstellensatz thing.
Is this combinatorial Nullstellensatz thing also, does it appear in the MIP star equals RE proof? Like in there? Is this
that I know, not that I know of?
I think it does appear there in some form. I didn't see the actual statement, but I saw
Maybe they use it as a black box, but they use like maybe it is inside one of the black boxes of the PCPs, right? Like this.
Yes, except I actually don't think it's a black box. Maybe they don't say it explicitly, but they actually do define these FI polynomials at some point, and use them to prove that some polynomial is 0 on Boolean inputs. They do that. Okay, so fine. So we proved the combinatorial Nullstellensatz, and now if I have access to this F prime, I can also ask for access for F1 up to Fk. And now I want to verify that F prime is 0 on Boolean inputs. What do I do?
You evaluated some random point, and you also verify that the FIs are of degree at most d-2?
Yeah, so I need to somehow verify that these are actual polynomials of degree d at most or d-2 at most. This we do by the low degree test, which I didn't really explain in detail, but I at least made the statement last time. So for now, we can assume that these are actually low degree polynomials. And then all we need is to verify that F for random input X, that let's call this equation, I'll just copy it. I'll maybe copy it and then call it by name. Oh, that's not what I wanted. Just a second. Let me just handle the copying and pasting parts. Copy. Yeah, so I pick a random point and I verify that these things are equal. And because on both sides I have polynomials, of low degree, if they are not equal, then with very high probability, I will not get an equality. And if they are equal, I will get an equality. And then I will be more or less persuaded that F is 0 on Boolean inputs. Yes, now there's a question.
So just to make sure, Fi are multivariate polynomials, right?
Yeah, so the Fi's, yeah, you can see here, the Fi's are of X. So Fi is from F to the K to F, because it is obtained by dividing a polynomial of this form by a polynomial that only depends on one variable, but still you get a polynomial over all the other variables. Right, so this is, yeah, so if the only statement that I needed to verify was that this polynomial that I have access to has the value 0 on all Boolean inputs, then I solved the problem. But what I really need to verify is other things. So let's talk about this first. How do I verify this? So let's put it here. Yeah, so how do I verify something like that? It's not very difficult. First of all, the simple thing is that
if you take E-1, you get the same idea as before, right?
Right. So yeah, one thing that is obvious is that to verify that something is 1 is as easy as to verify that something is 0. I can just, all I need is to, yeah, so this I do by evaluate this thing at a random point and verify this equation. So let's call it star. But with, so I have this thing at a random point that's not X, that's I and alpha and beta and gamma. So I will, I evaluate it at a random I, alpha, beta, and gamma. I get a number and then I remove 1. And hopefully I get something which is always 0 for Boolean inputs. So for this to work, I need the following. So here's something to note. This is of degree at most something. I claim that as a function of I and alpha and beta and gamma, this is a low degree polynomial. What is the degree of this?
M times L something, asymptotic yes. In that?
Yeah, at most n times L. It's not even asymptotic. It's really bounded by n times L. And that's because, how did I get this? F hat is a formula that computes a polynomial of degree n at most. That we already said. We get F composed with A by replacing the last 3 variables of F with A of those variables. And A, we already said, is of degree at most L because it's a multilinear function. So we replace 3 variables of a polynomial by this A, which is of degree L. Yeah, the degree of what we get is at most n times L. So this is a polynomial of degree n times L. And also, of course, this polynomial, if I also include this -1, this is also a polynomial of degree at most n times L. And of course, yeah, so what polynomials do I need to be able to access? So given access to A hat and also some G1 up to G M plus 3L helper polynomials. Right, because this is a polynomial in M plus 3L variables, and I want to verify that this polynomial is 0. So I need to have this number of helper polynomials, and I need to be able to evaluate this polynomial at a random point. And for this, it's enough that I have access to the polynomial A hat, because that allows me to, I choose I and alpha and beta and gamma at random. Given alpha and beta and gamma, I can compute A hat of alpha and A hat of beta and A hat of gamma. And then all I need is to plug it into, I need to plug I and alpha and beta and gamma and A hat of alpha, A hat of beta, and A hat of gamma, which I got from accessing A hat. I need to plug all of this into the formula of F hat. This formula I have in my hands, I built it. So I don't need access to anything else. If I have access to a hat and the helper polynomials, I can verify the statement. Okay. Yeah, so is this fine? So I have access to a hat and to these G's. And I use the access to a hat to compute a hat of alpha and a hat of beta and a hat of gamma. And then I plug everything into the formula that I have for f hat that I got from being given the Boolean formula for f. So I evaluate at a random point, I evaluate all the G's at the same point, and I verify this star equation. Okay, so unless there are questions, I have only one more thing to take care of, and maybe one thing that maybe now I'm going to be questioned about. Yes.
Yeah, I just want to say that at least heuristically, it's reasonable what you've done at the last point, right? Like you chose a random clause in your free sat. This is the way I think of choosing a random I, right? Mm-hmm. And if you pick the correct alpha, beta, and gamma, you are actually checking the correct clause, and then you need access to the proof, to the assignment. This is a hat. And the way you actually check that this is a correct assignment is using these G's, these helper G's, right?
Right, but the one point here that is important is that, you know, if I do it once for a random alpha, beta, and gamma and I, it is sufficient. No, and I get, and I get a positive answer. Then, except for a small probability, I know that all the clauses are satisfied. Not just the clause that is described by the specific I that I chose.
This is because the polynomials are of low degree, right?
Because the polynomials are of low degree, right? So if the polynomials, because the polynomials are of low degree, then either I will get inequality with very high probability for a random I and alpha and beta and gamma, or all the polynomials are just equal, and then I'm guaranteed that f composed with a minus 1 is identically 0 on all Boolean inputs, on all alpha and beta and gamma and I. Yeah, so this is the power that I get by using polynomials, the fact that equality can be checked very, very efficiently.
Okay, so I have another question. So Michael mentioned that at some point that where you needed the large field. Can you repeat where we needed the fact that the field was very big?
Yeah, so we are using the fact that I'm comparing. No, I have this polynomial f. In this case, the polynomial f is just f hat composed with a hat minus 1. And I check that it equals the sum that I get from the values of the other polynomials, and I check it at one point. I want to be able to say that if I get equality with high probability, then this means that this holds not just for a random point, but for all points.
You need the Schwarzschild, right?
So you need Schwarzschild. I need the fact that I need the field to be large enough so that I will say I will be able to say that if this holds with high probability, it actually must hold as an identity. Okay, so let me just say the last thing, which is actually quite simple. This was to verify, so we verified this. Now we want to verify that this is true. 0, 1 to the something, that this is always either 0 or 1. So how do we verify that? The answer is just that we verify at a random x that a of x times 1 minus a of x. Well, never mind the random x. What we actually verify is that this thing is 0 for Boolean inputs. All right, so yeah, hats here. So if this was a low degree polynomial, then now this is a low degree polynomial. The degree is smaller than 2L. So this is a polynomial of small degree. And we know how to verify that a polynomial of small degree is identically 0 on Boolean inputs. All we need is to be able to have the helper polynomials, which we can. We just ask the provers to provide us. And we also need to be able to access this polynomial at a random point. But we can, because we have access to a hat. So we just access a hat at a random point x, and then we can compute ourselves a hat of x times 1 minus a hat of x. So we compute it ourselves after one access to a hat. And then we use the helper polynomials to check that the two values are equal at x. And for this to be true with high probability, it must be that this polynomial is actually equal to sum of xi times 1 minus xi of times the helper polynomials. And this means by the Null-Stellensatz that this polynomial is identically 0 on Boolean inputs.
Guys, so just checking that I'm with you, the success probability, okay, like we said that we need 1 minus poly. This is again coming from choosing the field of the right size and checking that.
Actually, the way that I showed it so far, we can choose the field to be, say, n times L times 10 to the 6. And then the probability that we'll accept a wrong statement when we verify, for example, when we verify this, the probability that we accept a wrong statement is actually going to be very, very small, right? Let's go back to this star equation. Where is it?
You say it's not even 1 minus poly, it's actually...
Yeah, it's actually 1 over 10 to the 6, 10 to the 6 or whatever. Right, because these polynomials if they are not equal, they are going to be equal on very few points. The reason that the overall success probability can actually be close to 1 is because of something that I skimmed over, and which is I showed how to verify property 1, and I showed how to verify property 2. But verifying both of those required me to access a hat. And I only have one access to a hat. It's just one.
Okay, we lost Guy.
Michael, maybe you make use of the time just to say what's next, because we are already over time.
Yeah, so okay, so thanks, Guy. He doesn't hear us probably, but thank you very much for the talk. So next week we will proceed with our review of MIP star is equal to RE. Like I stopped at some point, and we will proceed both clarifying some things that weren't clarified well enough when I previously showed that point, the self-testing point, and proceed a bit to where PCPs get into it and other ingredients in the proof. This is next week. And at the end of the semester, so I don't know if I'll take 1 week or two for what I just said, Alon and Daniel, who are here, will maybe talk more about the connection between the QEP conjecture and Cyrilson's problem, and modulo the fact that QEP is equivalent to cone. We will see another way where MIP star is equal to RE refutes cone's embedding problem. So this will be more mathematics oriented. Okay, so thank you all. I'll stay here if Guy maybe comes back, but thanks, and thank you, Guy, again.
We thought, bye.
Bye. Thank you, Guy.